everyone, welcome back. In this particular video, we will be discussing the problem GCD of two numbers, which is a question based on mathematics. We are given two numbers A and B. What we have to do is we have to find the GCD of these two numbers using recursion. GCD means greatest common divisor, or it is also known as highest common factor, HCF. So we have to find out HCF or GCD of two input numbers, which will be of 64-bit numbers. Why? Because both of these numbers A and B will be from 1 till 10 to the power 18. So it will be of a long data type in some of the languages. So two numbers GCD should be figured out using recursion. For now, let's just see the sample input and output, and then we will also discuss about various more kind of corner cases. If there is two numbers, 8 and 20, what will be the GCD of 8 versus 20 or 8 and 20? It will be 4. What will be the GCD of 80 and 80? It will be 80 only. So if I will just copy the test case, let's say GCD of 8 and 20, the output is 4. GCD of 80 versus 80, it is nothing but 1. What is GCD or how to calculate GCD? How to calculate greatest common divisor? So we will go by the name only, that is greatest common divisor. We need the greatest number, the maximum number, which is a divisor, which is a factor of both the numbers, which are A and B. GCD of A comma B should be such a number, let's say it is C. C should be such a number which is a factor of both A and B. That is A modulus C should also be 0. It means A modulus C should give me 0. Why? Because A modulus C is nothing but on dividing A by C. If it is giving 0, it means A is a multiple of C, or C is a factor of A, or you can say A is divisible by C. Similarly, the B factor, B should be a multiple of C, or you can say C should be a factor of B, or B modulus C will also be 0. If both of these conditions are true, if A modulus C is also 0, as well as, let me just write and here, as well as B modulus C is also 0. But such a number C should be the maximum number possible, and it should be common. Common means it should be and. It means it should be a multiple, or you can say a factor of both A as well as B, or you can say A and B both should be multiple of C. So such a number which is a factor of both the number and which is the maximum such number, it is the greatest common divisor. So if I will try the GCD of 8, 20, what are the factors of 8? Factors of 8 are 1, 2, 4, and 8 itself. These are the factors of 8. Or you can say 8 is a multiple of 1, 1 into 8, 2 into 4, 4 into 2, 1 into 8, or 8 into 1. What are the factors for 20? It is 1, it is 2 again, it is not 3 now, it should be 4, because 4 into 5 is 20, then it should be 5, then it should be 10, and then it should be finally 20. So, is one common factor among both 8 and 20? Yes, but is it the maximum one? Maybe it can be, maybe it can't. Let's try for next. Is it 2 common for both the numbers? Is 2 a common factor? Yes, common factor, but is it the maximum one? It might be. What about 4? It is a common factor, but is it the maximum one? I'm not sure. 8. It is a factor, but not a factor of 20. It is a factor of 8, but not both. So it is not common factor or common divisor. What about 5? Again, it is not common divisor. Same for 10, same for 20. So the highest common factor or the greatest common divisor is nothing but 4. That's why the answer is 4. What is the answer for 80, 80? Since both numbers are 80 only, whatever factors will be there for A, same factors will be there for B, because both numbers are same. So the highest common factor will be the number itself, because we can say 80 will be getting divided by 80 completely. But what if, let's say, a corner case, or not a corner case, but a test case where we can have a dry run, a little bit of dry run is, what will happen for, let's say, 32, and the second number is, or maybe not let's not take 32. Let's take actually maybe 18. And the second number which we are taking is nothing but, maybe we can say 24. Let's take 24. These two numbers we are taking, and we need the highest common factor. So what are the factors of 18? 1 is a factor for sure. 2 is a factor because 18 is an even number. 3, yes, 3 is also a factor. What about 4? No, 18 is not a multiple of 4. What about 5? No, 18 is not a multiple of 5. What about 6? Yes, surely it is. What about 7? No. What about 8? No. What about 9? Yes. What about after 9? There will be, I guess, directly 18. What about 24? There will be 1, there will be 2, there will be 3, there will be 4. Also, there will be 5. No, there will be 6. Yes. There will be 7. No. 8. Yes, 8. 8 into 3 is 24. Then there will be not 9. There will be not 10. Then I guess directly 12 will be there. And finally 24 will be there. And what is the factor which is common? All these factors 1, 2, 3, 6. 1, 2, 3, 6 are common. But the highest common one is the 6. So answer is 6 for these two numbers. But what is the approach which we are going to follow if we are separating out recursion for now? What can be a brute force solution, approach one solution? We can say that let's start from the smallest number possible, which is 1, and let's try to go to bigger numbers, go to bigger numbers, go to bigger numbers. Or maybe we can start from the biggest number itself. What is the biggest number? Let's start from 18. Why? Because GCD of 18, 24 can never be more than 18, because all the factors of 18 will be less than equal to 18. So start from the minimum of both numbers. Start from minimum of a comma b. That is 18 in this case. Check whether 18 is a factor of both numbers or not. No, 18 is not. So let's try for 17. 17 is also not. 16. No, it is not factor of both numbers. 15, not. 14, no. 13, again no. 12. Although 12 is a factor of 24, but it is not factor of 18. So it should be both. Common divisor, no. 11, no. 10, no. Similarly, 9, no. Although it is a factor of 18, but not a factor of 24. Similarly, for 8, although it is a factor for 24, not for 18. 7, not factor for both. And finally, if I will go to 6, yes, it is a factor of both 18 and 24, because this formula will be true. That is, a modulus c will also be 0, as well as b modulus c will be 0. 18 modulus 6 as well as 24 modulus 6 will give you 0. So we will print 6, or we can say return 6. But what is the overall time complexity? As you can clearly see, overall time complexity will be linear. Why? Because we will be going to each and every number. So it will take order of minimum of a comma b time, but it is linear in nature, we can say. Is there any better solution? And according to the question, we have to solve it using recursion. The answer is yes. We will be actually applying the algorithm which is known as Euclid's algorithm. Approach 2 is nothing but the Euclid's algorithm. What is the Euclid's algorithm to actually calculate the GCD of two numbers? Let's take the same example, which is nothing but 18, 24. What we will do, we will actually do long division. Euclid is nothing but long division. We will start from 24 as, let's say, the numerator, 18 as, let's say, the denominator. We will try to divide 18, the 24 by 18. Obviously, there will be some quotient, there will be some remainder. So what will be 18 when it is getting divided, or when it is the divisor and 24 is the dividend? We can say 1 will be the quotient. We are not actually caring for the quotient. What we only need is the remainder. So 24 minus 18 will give you 6. Now what to do with 6? We have to do the division only till the point we are getting the remainder 0. We will continue the division recursively again and again till the recursion or till the division will actually give me 0 remainder. So right now the remainder is not 0. We will still continue. But what will be the new quotient? What will be the new divisor and dividend, or you can say numerator and denominator? The previous remainder will become the new denominator. The previous denominator, or previous remainder, not denominator, but previous remainder will become the new denominator. And what about the new numerator? The previous denominator will now come at the place of the numerator. 18 will now become the numerator. So if I will divide 18 by 6, what will be the remainder? Remainder will be 0 only, because 6 into 3 is 18 and remainder will come 0. And if remainder is coming 0, we will stop. But what is the answer? What was the answer of 18, 24? It was 6. So the last denominator will be the answer. The denominator, when we can say the remainder is 0, is the answer, or you can still say continue. Continue means the denominator is a 0. That is the previous remainder. And the previous denominator will become the new numerator, that is 6. And as soon as the numerator becomes 6, or as soon as the denominator becomes 0, we can say the numerator is the answer. The numerator is the answer. In this case, the answer is 6. The GCD of 6, actually not 6, but 18, 24 was 6. Let's just see it for one more test case. Then we will try to give a proof, although starting with a proof only, it will be very difficult to swallow. But once we are having some dry run, then seeing why it is working, that will also be clear. So what we are going to do is, we are going to say, let's just find the GCD of two numbers which are maybe 32 and 48. Let's just try for these two numbers, 32 and 48. So obviously, A can be anything, B can be anything. Here, A was 18, B was 24. Here, I am taking A as 48, B as 32. That is, B is the numerator, A is the denominator. Or you can name these as A instead of A and B, you can name this as numerator, denominator only. But let's just say that for now, we are taking B as the numerator, A as the denominator, or maybe num as 32, then that is denominator as 48, and continue. If I will try to divide 32 by 48, what will be the quotient? Obviously, 48 is bigger than 32. We will not be able to divide even by 48 into 1. So complete 32 will be the remainder. And if complete 32 is remainder, what will be the new numerator? What will be the new denominator? The previous remainder will become new denominator. And the previous denominator will become new numerator. That is, 48 will come under the division. It will become numerator. That is, if somehow the numerator is smaller as denominator when compared in between numerator and denominator, if numerator becomes smaller, in the next step itself, the swap is happening. That is, the numerator is becoming denominator, denominator is becoming numerator. So answer will be same. GCD of 48, 32 will be same as GCD of 32, 48. What if we divide 48 by 32? The quotient will be 1 because we will be able to subtract 32 and remainder will be 16. Now, what to do with this 16? We can say this remainder is not 0, so we will actually continue the division. This remainder is going to become the denominator for next iteration, and the previous denominator will become numerator, and we will try to divide. 16 will actually completely divide 32, and remainder we will get will be 0. And if remainder we are getting is 0, then actually if I just continue for one more step, we will say the previous denominator will become numerator. As soon as the denominator is 0, we can't divide by 0. And if we can't divide by 0, whatever is the numerator, that is the answer. So GCD of 32, 48 is nothing but 16. For both of these numbers, the biggest multiple, which is factor of both, is nothing but 16. Biggest number, which is a factor of both 32 and 48. But main thing is, why is this approach working? The reason is, if I will ask you what is the GCD of 18, 24, we already calculated it is 6. But what is the GCD of 6, 18? What is the GCD of 6, 18? It is also 6. What is the GCD of 0, 6? You can't say what is the GCD of 0, 6 because 0 can't be, or we can't find actually the multiples or the factors of 0. We can't divide any number by 0. So these two are same. What about this? GCD of 48, 32 as calculated, it is 16. What about 32, 48? It is also 16. What about 16, 32? This is also 16. And what about the last number? Obviously, in that case, we can't divide. So every time it is 16. Both of these numbers, if we are taking GCD of them, it will give the same number as a 16. So answer of this division is same as answer of this division. Or you can say GCD of this is same as GCD of this, is same as GCD of this. And why is this working fine? We can say that GCD of A, B, GCD of A, B. If I am actually subtracting A from it, that is, if I am saying, let's say, for this number, if I am subtracting A from this is A, this is B, let's suppose. So I am subtracting A from it. What will the number become? It will become B minus A. If this is A, this is B, this will be B minus A. So GCD of A, B is the same as GCD of B minus A, comma, the A number again, GCD of A, B is the same as GCD of B minus A, A. This is a reconciliation, a property based on GCD. If you will explore more about highest common factor, you will see this property is very common under all the textbooks, whichever will teach you about Euclid's algorithm. So due to this recurrence relation or due to this formula, the Euclid algorithm is working fine, but we will actually not use this formula. Why? Because we will not subtract by one point at a time. We will not just subtract 18 every time. If we are able to subtract 2 times 18, we will subtract 2 times 18. See, if let's say this was, instead of 24, if let's say it was 40. So in that case, we can subtract 2 times 18, which is 36 from 40. No need to only subtract 18 and then again subtract 18. So the thing is, we will be using some other recurrence relation. What will be a shorter variation where we will be able to actually reduce the time complexity? The shorter variation will be GCD of A comma B as given in the dry run. GCD of A comma B or numerator comma denominator. Let's suppose A is the numerator, B is the denominator. Will be same as the GCD of which two numbers? The previous denominator will become numerator. That is first parameter. First parameter we are assuming it is numerator. And what will be the new denominator? New denominator will be the remainder on dividing numerator by denominator. That is A modulus B. So denominator will be A modulus B. The remainder when dividing A by B. That will be the new denominator. So we will be actually working on this recurrence relation, or we will be using recursion. We will be solving recursion using this formula. So if obviously both A as well as B are not zero, then we can use this formula. But what will happen if either A or B will be zero? If A is zero, it means actually we can say the division is done. If somehow we are able to reach to zero, the division is done either on A or B. If let's say we are having A as zero, then we can say B is the answer. Or if other ways also around, that is B is zero, then we can say A will be the answer. So let's just say that if A is zero, then B is the answer. Or if B is zero, A is the answer. If B is zero, then A is the answer. And if it is not, then we will just simply say, use this formula. That is GCD of A comma B will be the GCD of A comma A modulus B. So given this recurrence relation, only these three lines of code will be required. And actually, even if you remove this line, still the code will be correct. Why? Because as you have already seen, GCD of A comma B is the same as GCD of B comma A. So nevertheless, in the next step, if A will be zero, in next step B will become zero. So no need to handle this case. You can just handle this one and you can just handle this one. Or you can do vice versa also. That is, you can handle the second case. No need to handle first case. Let's just remove the first case. Anything will work fine. If B is zero, return A and then return A comma A modulus B. So only these two lines of code will be there. Let's go to the code. Let's just write, first of all, if B is zero, then just return A. That is A is the answer. If not, then just return the GCD of what? Of A comma A modulus B. That is, the previous denominator will become new numerator. The previous denominator will become new numerator. Actually, we have written something wrong. Why? The previous denominator is becoming new numerator. If I am taking the denominator as B, it is going to become new numerator. So it is B, not A. Here also it is B, not A. And the new denominator, what will be new denominator? It will be the remainder, A modulus B. That is correct. So B comma A modulus B. Now, these two lines are there. But what is the time and the space complexity associated with this code? See, for GCD of A comma B, if we are using this recurrence relation, what we are trying to do every time is we are trying to subtract the biggest multiple of smaller number, from 24, 18, from 18, 6 into 3, biggest multiple of smaller number. So every time we are subtracting biggest number, we are actually going in logarithmic time complexity. We are reaching log of minimum of A comma B in nature. Obviously, the proof is very lengthy and also not required, but surely we can say that it will come out to be logarithmic. The number of steps, the number of iterations, the number of divisions which we require will be only logarithmic in nature. This will be the time. What about space? Space will also be logarithmic. Why? Because we are using recursion. It means recursion call stack space will be required. So both time and space will be logarithmic. We will be discussing the code of the problem GCD of two numbers. We have already written the instruction manual or the pseudocode. It was just containing two lines. So let's just directly jump on to writing the code itself. So if B is zero, we have to return A, that is denominator is zero. So numerator is the answer. Otherwise, recurrence relation will be there. A comma B, GCD of A comma B will be same as GCD of B comma A modulus B. It means the previous denominator will become new numerator. First parameter is numerator, second parameter is denominator. And the remainder when dividing A by B will be the new denominator. So let's just run this code to see if my code is working fine or not. For sample test case, there are two test cases, 8, 20, 8, 80, 80. Yes, output is correct. Let's just try it for some more test cases, 8, 20, 80, 80. Let's try for 16, 35. or maybe 34, and let's try for 18 comma 32. So let's see if the output which we are getting is what we need. It is taking some time to run. Let's wait. Yes, so output is 2 and 2 in both the cases. The highest common factor in both the pairs will be 2 only. Let's just submit and it should give me correct output for all the test cases. Hopefully, it is taking some time to run. So let's wait for the output. And all the test cases are working fine. What is the time complexity of this code? A comma B going to B comma A modulus B. Every time we are trying to divide the number by the highest factor of both A and B or A modulus B, we are actually going in logarithmic fashion. So overall time complexity will be log of minimum of A comma B. This is Euclid algorithm. You can see the proof in one of the follow-ups mentioned in the problem, or maybe you can search it on your own on Google and you will be able to find the answer that why it is logarithmic. But at least when it comes to the DSA basics, you can just cram the part that it is logarithmic in nature, or just try to see some dry runs that the number of iterations will be very less, even if the both numbers A and B are very, very large. So with that, we will be wrapping up this video. We will come with a new video with a new problem. Till then, bye bye.